All right, it is the 15th of September 2025, approximately 1:55 p.m. Now let's get into the exercises of Chapter 3. So, start out with 3.1-1. So we are asked here, modify the lower bound argument. Oops. For insertion sort. Insertion sort to handle input sizes. That are not necessarily a multiple of 3. So intuitively, in the original omega of n squared argument, the array was split into these 3 equal thirds when n was a multiple of 3, right? So for arbitrary n, just take the largest floor function of n divided by 3 elements and go ahead and put them in the leftmost block. They will still have to travel through roughly n divided by 3 positions, right, to reach their final places in the sorted order, and this would give the same quadratic bound. Now, more rigorously, let's say let m equal floor function n divided by 3. It's supposed to be an n. Place the m largest elements in the first m positions. Now, in the sorted array, they must occupy the last m positions. Oops. So each of these elements of these m elements well, they move through at least n open parentheses n minus 2m close parentheses positions. I don't know why I keep on doing that. Okay, so, and this is the middle block, right? The middle block. One step at a time. Therefore, the total number of shifts performed is at least m times, open parentheses, n minus 2m, m times n minus 2m, which is what we have there. Gonna have to get more board space. And since n minus 2m is greater than or equal to m, we obtain m times, open parentheses, n minus 2m, close parentheses, is greater than or equal to m squared. And this, well, this is equal to the floor function of n divided by 3 squared, which is equal to omega, big omega, of n squared. So the worst case running time of insertion sort is big omega of n squared for all n. Not just multiples of 3. All right, let's move on to the next exercise here. So let me get there. So for exercise 2, 3.1-2, we have using reasoning similar to what we used for insertion sort. Analyze the running time of the selection sort algorithm from exercise 2.2-2. Now, if I'm remembering correctly, what we had for that exercise was this. We had selection sort, selection-sort, parameters a and n. For the first line, we had for I is equal to 1 to n minus 1 to min idx equal to I, line 3, for j is equal to I plus 1 to n, for if A indice J, array A with the indice J is less than the same array with indice min IDX. And then line 5, we had min IDX is equal to J. 6, swap the array of A's indice I and the same array with the indice min IDX. So how do we go about analyzing the running time of this? Well, let's get right back to it. Well, actually, before I begin, let's just go over the intuition. So on pass I, selection sort scans the unsorted tail. So the array indices I through n to find the minimum, and then swaps into position I. The scan length is about n minus I, regardless of input order. So every pass, well, that costs linear time. Summing a decreasing linear cost across n minus 1 passes, that yields a quadratic total. So best case doesn't help. You still scan the whole tail to certify the minimum. So let's get into this more rigorously about what I'm talking about here. So let the outer loop index I range from 1 to n minus 1. And so in each case, no, in each pass, selection sort must determine the minimum element of the subarray A indices I to n. So any comparison-based method for finding a minimum among the interval, well, actually, among open parentheses n minus I plus 1 items, close parentheses items, requires, so the minimum among n minus I plus 1 items requires at least n minus I comparisons. I think I can just say that without saying the parenthetical. So, therefore, the algorithm performs at least the summation from I equals 1 to n minus 1 of n minus I, which is equal to n times n minus 1, n times open parentheses, n minus 1 close parentheses over 2, which is equal to big omega of n squared comparisons overall. at the least. All right, I'm gonna make more board space to complete this. So a standard implementation performs that many comparisons. In addition, to at most one swap per pass. This gives us the matching upper bound, summation I is equal to 1 to n minus 1 of n minus I is equal to theta of n squared. So because this comparison count is independent of input, input arrangement, the best case average case and worst case running times well, those are all theta of n squared. Swaps occur at most once per pass, totaling n minus 1. So we've analyzed the running time of the selection sort algorithm from exercise 2.2-2. So let's go ahead and move on to the next exercise. So let's take a look at that. So we have 3.1-3. So let's suppose that alpha is a fraction in the range 0 less than alpha less than 1. Now let's show how to generalize the lower bound argument. For insertion sort, which is kind of what we've already been doing. But insertion sort. To consider an input in which the alpha times n largest values start in the first alpha n positions. So for this, we are specifically asked, what additional restriction do you need? Not you specifically, but just, the reader in general need to put on alpha. Then we're asked another question. What value of alpha maximizes the number of times that the alpha times n largest values must pass through each of the middle. That's 3 questions in one, right? But that's fine. Open parentheses 1 minus 2 alpha, close parentheses times n, array positions. All right, so intuitively we'd want to place the largest alpha times n items to the leftmost alpha times n slot. In a sorted array, these elements must end up in the rightmost alpha times n slot, so each one must slide right through the entire middle block. The middle block has length, open parentheses, 1 minus 2 alpha, close parentheses, n. So every one of the alpha times n large elements contributes at least, open parentheses, 1 minus 2 alpha, close parentheses, n single shifts. The total then would be on the order of alpha times, open parentheses, 1 minus 2 alpha, close parentheses, times n squared, which is quadratic. This argument only makes sense if the middle block exists, that is non-negative length, right? So forcing alpha to be less than or equal to 1/2. Maximizing the quadratic coefficient alpha times, open parentheses, 1 minus 2 alpha, close parentheses, occurs at alpha is equal to 1/4. And we can actually look at that a bit more rigorously here. So let's see. Assume n is large and use the floor or ceiling function if needed to handle integrality, which I mean, like, I don't know if I really need to put this. Just even make a little note of it. So it's like assume n is large and use these functions if needed to handle integrality. So which I might not even really need to put this and part. But suffice to say, maybe, which I can't remember, which does not affect asymptotics. We'll see. So let's partition. Actually, we might partition the array indices into 1 all the way to alpha times n elements. So 1 dot 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 comma alpha times n. So we have left block of size alpha times n. We have this middle block here, which is alpha times n plus 1, comma, dot, 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 comma, open parentheses 1 minus alpha, close parentheses n. We have the middle block of size open parentheses 1 minus 2 alpha, close parentheses n. And we have this third block here. So open parentheses 1 minus alpha, close parentheses times n plus 1, comma, dot, 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 comma, n. And this is the right block of size alpha times n. So let's place the alpha times n largest elements in the left block in arbitrary order. Now, almost out of space here completely, so we'll probably have to wipe the board here pretty soon, but in a sorted array, these elements, these alpha times n elements, end up in the right block, at the right time, in the right block, right? Disorder and order. Okay. Confined to both right and left block. Ooh. Now, I gotta erase the board. Now, let's see here. In insertion sort, this is what we're talking about. Insertion sort. Each unit shift advances an element by exactly one position. So each of these alpha times n elements must execute at least open parentheses 1 minus 2 alpha close parentheses n shifts to traverse the middle block. So the number of shifts, I just shift my pants. No, that's horrible. Shifts is at least open parentheses alpha times n close parentheses times open parentheses 1 minus 2 alpha close parentheses times n close parentheses, which is equal to alpha times open parentheses 1 minus 2 alpha close parentheses n squared. Therefore, the running time is omega of alpha times open parentheses 1 minus 2 alpha close parentheses times n squared. Now let's go to that restriction. Okay. That's the first part. Now let's go on to the restriction part. So for the restriction on alpha, to have a non-negative indeed non-empty for a non-trivial bound, middle block we require 1 minus 2 alpha greater than or equal to 0, which is to say alpha is less than or equal to, less than or equal to 1/2. And so, well, for a strictly positive bound, from this specific pass through the middle argument, let's take alpha to be less than, strictly less than 1/2. Now, what value of omega maximizes the number of times that omega n largest values must pass through each of the open parentheses 1 minus 2 alpha close parentheses n array positions? Well, let's take a closer look at that. So, maximizing the coefficient. So, to have a non-negative, whoopsies, I almost just went back into talking about the previous part. But let's define f of alpha to equal alpha times open parentheses 1 minus 2 alpha close parentheses on 0, which is less than or equal to alpha, which is less than or equal to 1/2. Right. So then some f prime alpha equal to 1 minus 4 alpha. So the unique maximizer, well, let's see. Yeah, so the unique maximizer is alpha to the asterisk is equal to 1/4. And this is with f of alpha to the asterisk, which is equal to 1/4 times open parentheses 1 minus 2 times 1/4 close parentheses, which is equal to 1/8. Right, so we're looking at this iteratively, which is why we have the asterisk, right? So we get that the unique maximizer is equal to 1/8. So therefore, the bound is maximized at alpha is equal to 1/4, yielding at least 1/8 n squared shifts, which is to say that is big omega of n squared time, right? Okay, that's it for the 3.1 exercises, I believe. So we'll go on to the next ones.